Hello, welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Kelly Schmidt, lead tutor for statistics at the Learning Center. In today's video, we will explore a few of the fundamental topics and skills related to Chapter 6 and probability distributions that will help you to be successful in the course. Let's get started. First, let's look at what a discrete probability distribution is. This table is an example. The first column gives us the 4 possible values for some random variable x. For example, the data in this table might be representing the results you would expect to get if you had spun a spinner that looked like this. You have a 51% chance of landing on a 3, a 38% chance of landing on a 2, a 10% chance of landing on a 1, and only a 1% chance of landing on a 0. There are 2 main conditions that our probability distributions have to meet. First, all of the values in the p of x column must add up to be exactly 1. Second, none of the values of p of x can be negative. If we think of this in terms of the spinner, it makes sense. We can't have a total of more than 1, which would be more than 100%. It wouldn't fit into our circle. For the second rule, a negative probability wouldn't make sense either. The lowest possible probability is 0. So now, given a discrete probability distribution like this, we can calculate both the mean, also known as the expected value, and the standard deviation using these formulas. To find the mean by hand, we would need to plug the values for x and p of x into these formulas and find each answer. However, StatCrunch lets us do this much faster. For practice, let's find the mean and standard deviation of the following discrete probability distribution using StatCrunch. First, we open up our data in StatCrunch. We have our x column labeled x and our probability column labeled p of x. Now click on Stat, then Calculators, then Custom. Enter the column name, x, under Values In, and then enter the probability column, p of x, under Weights In. Now click Compute. This will open up our results window. We can see that our mean here is 2.39, and our standard deviation is 0.7056. Next, let's look at an example of how this might be useful in the real world, in gambling. In a game of roulette, a player can place a $15 bet and have a 1/38th probability of winning. If the player wins, they are awarded $525. What is the expected value of the game to the player? We start by making a discrete probability distribution for this situation. The probability of winning is 1/38th, and the probability of losing is 37 out of 38. If the player wins, they're awarded $525. So 525 is the value of our variable x in the case of a win. If the player loses, they lose their bet of $15. So the value of x in the case of a loss is negative 15. To find the value they would expect to win on this game, we need to find the mean of this probability distribution. We can do this on StatCrunch by inputting these values and following the same steps we did before, or we can simply find the value by hand, since this is a small dataset. Recall that the formula for the mean of a discrete random variable, also known as the expected value, is mu of x equals summation of x times probability of x. While this may sound intimidating, all it means is that we need to multiply each x value by its associated probability and add the results together. For example, here we take the first x value, 525, and multiply it by its probability, 1/38. Then we do the same for the second value of x, negative 15. We multiply it by its probability of 37/38. Finally, we add everything together and we get a final answer of negative 0.79 or negative 79 cents. Interpreting this, we would say that we could expect to lose an average of 79 cents per game if we played this game many times. Next, we can look at how the concept of probability distributions can be applied to lottery problems. Let's say that we have the problem here. Given the following information about a fictional lottery, how big would the grand prize need to be so that a person might expect to break even with a purchase of a $1 ticket? Based on the table here, we know that there's only one grand prize ticket available. There are 2 tickets in the pool that will win a person a $1,000 prize. There are 3 possible tickets that will win $5, but the majority of tickets in the pool, the 9,994 remaining, are all losing tickets. Total, we have 10,000 tickets in this lottery. To solve the problem, we start by setting up an equation. Expected value minus $1 is equal to 0. The left half of the equation shows the amount we expect to win, the expected value, minus the amount we spent to buy a ticket, $1. We set it equal to 0 because we're interested in the point at which we break even, where our profit is 0. Next, we find the probabilities associated with each outcome. There are 10,000 tickets total, so we divide the number of tickets in each category by this total. Now we use these probabilities to construct the formula for the expected value. After plugging in our values, we simplify and use algebra to solve for the value of our unknown grand. First, we multiply out our terms. Then we add 0.7985 to both sides. Then we divide both sides by 0.0001. This gives us our final answer of $7,985. So we know that our grand prize must be at least $7,985 before we can expect to break even playing this lottery. Alright, so I hope this gives you a good idea of some of the problems you might expect to encounter when working with discrete probability distributions. Thank you for watching this TutorTube presentation. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.